Alrighty, good morning, lads and ladies. Welcome back to Calc 1. I've got a few things to talk about today. It looks like we're a little bit short on people still, so let me switch over here. I'll take a second and get started. Before we get into the actual content, I want to talk a little bit about exam grades. Hoping we'd have more of the class here. Let me turn off my share real quick, see if I got something from. All right. Well, I guess it's going to take a minute for folks to filter in, either that or we've got some folks who just don't want to come in today, which is a shame. But perhaps we're feeling a little bit discouraged. So, sorry if I'm hesitating a little bit here. I'm trying to find the right words. The exam 2 grades were abysmal, and I say that with all the love in the world. But they were bad, guys. They were really bad. And that exam, there are some concerns about, when exam grades turn out this poorly. My first thought is always perhaps the exam was too difficult. Maybe there was something in there that made it extra challenging for one reason or another. So I compared it against some of the exam grades I've had from the past, and I looked at the questions and the statistics on the questions, discrimination indices and things like that. And I'm not finding much, to be honest here. Now, I would love to say that, oh, okay, here's this obvious like sticking point, too much trigonometry or too much logarithm stuff or something like that. But looking really carefully through the work, the things I'm seeing are largely algebra mistakes, or not knowing differentiation rules, things that really should have been taken care of by exam 1, if not the test itself, by the comments and the work we've done together since then. So I'm at a bit of a loss. Let's go ahead and get started here. I'll talk a little bit about what I intend to do. Let's say the 24th. So announcements. I'll put it right out there. The average on exam 1 is 47%. I'm sorry, exam 2, not exam 1. The average on exam 2 is 47%. And in all the years I've been teaching this class and other calculus classes, I don't believe I've ever seen this before. I genuinely haven't. There are a handful of special factors here, things that I'm trying to keep in mind as I reflect on this, and I hope that you will do some reflecting on this also. First, I get that COVID sucks. COVID has really kind of fucked higher ed. There's just so many things that we can do in person that we can't really do over this medium. For example, I can't see your facial expressions as we talk. So it's a little bit tricky to tell when folks are grasping material strongly versus having a difficult time with it, besides the feedback you give me, through email or in chat. But the kind of very human thing where you look out over the class and see whether people are looking frustrated or happy or bored isn't really an option here. And I get that. It's, I don't blame you for not having your video feed on all the time. I probably wouldn't if I were a student, because who the fuck knows what's going on in the background. And I also understand that the standards for a lot of other classes have slipped quite a bit over the last few years, or over the last few semesters. I've mentioned a few times in passing that my wife is currently taking some calculus classes at Santa Fe. And I've seen what those tests look like. I've seen a Calc 1 professor skip all of chapter 2. I've seen trigonometry and pre-calculus professors skip sections that I consider entirely vital. And I would put all of that under this COVID has fucked higher ed thing. Now, I can't say that those sort of losses in prerequisite classes fully explain this, because I've adjusted the exam. You see, I've taken out anything that required any use of periodicity or any use of symmetry. There wasn't anything like that on the test. The sort of subtle things that might get lost in a pre-calc or a trig class, they weren't present here. And I want to reiterate that the majority of the mistakes I saw were like algebra manipulation mistakes, and differentiation rule mistakes, like not being comfortable with the product rule or not being comfortable with the chain rule, making kind of fundamental but calculus-based errors there. And those are the sort of things that should not survive past exam one. Exam one exists precisely to weed those things out, to point them out to you, and to inspire you to fill whatever gaps might exist following the lectures preceding exam one. So, so there's a factor here that I think is relevant, but not those things. And those things were the majority of the things that ended up losing points. So I think another thing here is time management, right? Time management is critical. And under this bullet point, I'd like to talk about a few things, and I'm hoping that you guys take this to heart. Otherwise, I wouldn't burn lecture time on it. There are two areas where I see time management really stinging us on the test. First is managing the time during the exam, right? So I've been there before where you're taking a test online, and it's different than taking a paper test. When you take a paper test, the natural thing that we all do is kind of flip through the test and look at the questions and see, okay, this is what I know how to do. This is what I don't know how to do. So I'm going to go through and do the shit that I know how to do. And then I'm going to come back through and work on the slightly harder problems until I get stuck. And then I'm going to come through and work on the really hard problems. And I see that it's harder to do that online. I remember taking the GREs. The GREs, you could look at just one question at a time. You couldn't flip through the thing, and it was very frustrating. I do allow you to scroll through the test, right? It's not the case that you view one question at a time. And I want to remind you that it's super important to answer easy questions first. So as you would with a paper test, please, on all future exams, survey the test before you begin, right? Do not just go, okay, I'm looking at question one at the start, I'm going to solve question one, then I'm going to go to question two. That might feel methodical, it might feel kind of algorithmic and mathy, but I promise you it's not the way to do things. You want to look through the test, see what problems you know how to solve, knock those out first, then come back and look at the ones that you think you have some idea of how to solve. Knock out as many of those as you readily can, and then come back through and start working in order. There should really be like 2 layers of surveillance done during any test, regardless of whether it's online or in person. The other thing is managing time before the test, right? So unimaginably important. Well, I mean, we can imagine, but I'm using the word unimaginably here for emphasis. Unimaginably important to invest appropriate time preparing. There are all sorts of little cheesy slogans about preparation, and I don't want to give those to you in any condescending way, because God, I hated when people did that stuff when I was in high school. I remember there was this guy who would say proper prior preparation prevents piss poor performance, something like that. And I loathed that man because I felt like it was constant condescension. But there's truth in it. There really is. You see, about 3 of the exam questions came straight off the study guide. And you had the study guide for a week or so before the test. So there's really no excuse to not like destroy those questions. Those should be rock solid 100% from everybody because they're verbatim from the study guide. Another handful of questions came verbatim from the homework. Those should be easy 10 out of 10s because you've had a week to work on them before the test. So I get a little bit lost thinking about it. The conclusion I have to draw is that we either didn't solve the study guide and homework problems, or we didn't solve them honestly, right? Just worrying about getting answers on the page as opposed to really understanding them. Perhaps even looking up answers, which I know is quite doable. So these two time management things I want to really emphasize as being very, very important moving forwards. The COVID situation is difficult right now. I know it's hard coming to class in this setting. I know it's hard getting everything out of class that you would like to get out of class in this setting. But please take these two things seriously. Unfortunately, I have to answer this call, but I will be right back. Hello. All right, I got my COVID vaccine all set up. This is nice. Right, so these are the two main things. As far as I can tell, right, there's all these different things from COVID, and I'm trying to be very sympathetic about that, but there's also some obvious time management shit here. If I put 3 problems from the study guide on the test, you guys all need to be knocking those out of the park. There's no excuse for that. I don't normally do that. That's something that I'm doing to try and be nice, given the difficulty of the setting. The idea that you would have a 100% in the homework and turn in a 25 out of 25 study guide and then miss 3 problems that were verbatim from the study guide is frankly absurd. I love you guys. Please don't take this as me saying anything negative about you personally, but there are some gaps here that need to be fixed. I know that standards at Santa Fe have slipped a little bit and that it's entirely possible that your pre-calculus or trigonometry classes didn't cover everything in detail that they need to cover, but that's why we have this review material module, and I refuse to slip. We can't do it. In order to keep the value of your degrees, in order for your Santa Fe AA to mean something to UF for transfer purposes or some other university, or for whatever your terminal academic goals are, we need to keep these classes at the level they're at. To be honest, they're already before COVID way below the level at UF. I taught at UF for a few years before this. And we, with the understanding that it's a community college, remove some of the more challenging material and we reduce the pace a little bit. And that's normal, totally normal stuff. It's not anything to feel bad about. And it doesn't mean you can't get a rock solid education at a community college. I went to a community college, but it does mean that you need to take it seriously. You really do. And I think there's a possibility that we're not all taking this as seriously as we need to. Today being the deadline for withdrawal, I have a few things in mind. So first, here's something I've never ever done before. I'm curving the test. By 10 points. 10%. The high score was a 92, by the way. There were A's here. There were A's and B's. The distribution was not horrible. It's just that it was very wide. All right, so normally, I'll show you a histogram really quick, and this will be the last thing I say about this stuff. It's the stats. So the average is a 47. The high is a 92. The standard deviation, this is a measure of how spread out the scores are. Ridiculous. 16.27 is a massive standard deviation. And you see the histogram here. It's very, very spread out. Normally, we expect to see 2 peaks, one right around here and another one right around here. Instead, we see 2 peaks shifted about 20 points south. One right here at about 35 and the other one right here around 50. This is what's called a bimodal distribution for those of you who are interested in statistics. And it suggests a few things. First, we've got our sort of group of middle amount of studying. And then we've got a group of maybe a little less amount of studying. And so we see these kind of, you've heard of the bell curve, right? This is a two-pronged bell curve. And this is normal in calculus classes because generally we do end up with kind of two groups of students. We end up with groups of students who take the class really seriously and dump a bunch of time in. And those usually form a large peak somewhere over here. And then we end up with a group of students who are taking the class a little bit less seriously, maybe aren't math or science majors, but do it because they have to. And that usually forms another peak somewhere between 50 and 60. So what you're seeing is this distribution is shifted massively to the left. Still bimodal, but much less collection around the larger. So what I'm doing is curving the test by 10%. I looked at two questions. There were two questions that very few people got correct. And so I'm thinking of about half the points from one question, about half the points from the other question. There are two questions there whose average was around 50 that I would have expected to have an average around 90. And for those two questions, I'm compensating by curving the test by 10%. Yeah, so if you took the test after the test date, if you took a makeup test, those have not all been graded yet. The rest of those will be in today. So all the folks that took the test last Monday or whatever, those are all graded, and some of the makeup tests are graded, but not all of them are. So this is the state of things, guys. It is. I'll say this. I love you all. I really do. Right. I teach because I love teaching. I'm genuinely passionate about helping you learn mathematics, but you need to put in the effort. I mean that. I don't just mean sitting there staring at problems. I don't mean letting yourself get frustrated and then eventually looking it up on Chegg. I mean really struggling with the material until you get it. It takes struggle. Struggle is a good thing. We all must struggle. The only way you get good at shit, you guys, Adventure Time is, I'm getting old now, but the first step at being kind of okay at something is sucking at something. And it's okay that it sucks at first, right? But then you need to put in the grind to get good at it. If you've ever tried hula hooping or skateboarding or juggling or any sort of little skill thing, coding, if you've ever tried to develop a particular skill, then you know that at first it's not very good. But if you sink in the time, you can be shocked by how fast you become an expert. You can be the best person at Santa Fe in calculus inside 6 months. I'm dead serious. The gap between the person at Santa Fe who is worst at calculus and the person at Santa Fe who is best at calculus is like 6 months of hard work. Dead ass. So if you sink in this time, I swear to you, it will pay off. But you must sink in the time. Okay, that's the end of my rant. There's going to be a 10% curve, which is going to bring the average up to around 57, which is somewhere in the reasonable range. If you are trying to decide what to do with this class, if you're trying to decide whether to drop the class or stay in the class, I advise coming to office hours to talk with me. Outside of a handful of situations, if you are a student athlete or a Bright Futures or international student, then you need to make the decision today. But if that's not the case, if you're not one of those things, then we can actually have a little bit of looseness with the withdrawal day. I can manually withdraw you after the withdrawal day, and I'm willing to do that. As always, and as I mentioned in the syllabus, there are lots of ways I can be flexible to help, and I want to help, but you need to sink in the time. You really, really, really do. And if you don't have the time to sink in, or for whatever reasons, many of which are understandable, you just don't want to put in the time, then right now is not the moment to take calculus. So yes, of course, welcome to come to office hours. If you want an in-person office hour, yeah, we haven't talked about that since the beginning of the semester. If you want an in-person office hour, we can do that shit too, right? I've got permission to do in-person office hours. We just need to schedule them ahead of time and reserve a room so that we can do it socially distanced and safe. So yes, absolutely. I'll reserve A25. If you want to do an in-person office hour, just give me a day and a time. I'll reserve A25 and we'll sit on opposite sides of the room and talk and work problems. All that shit, we can do it. And I'm more than happy to do it. Okay. Questions from me about this stuff? I know this is an intimidating setting with me just bitching at you guys so hard about the test. But if you have questions about this stuff, let's get them out now. What are we thinking? What are we wondering? Is there anything that I can explain or put you at ease regarding? So Joe asked about IRL office hours, and yes, we absolutely can do those. Happy to do those. Just email me or Canvas message me the day and the time you want to do it, and I'll let you know. Okay, if there isn't anything else, then we are going to move on. So last time we introduced the definite integral. That is the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum I from 1 to n f of xi times delta x. And here, of course, the delta x is always b minus a over n, and the xi's are a plus I times delta x. I've given you a number of homework problems this week that require this definition. This object on the right-hand side should be familiar from last week's homework. I do want to just give you a little preview of those homework problems and discuss a little bit what methods and kind of approaches we should apply. So here, they're just more Riemann sum stuff, right? Just more areas with rectangles, although now our functions are allowed to sometimes be negative and sometimes be positive. Nothing magical there. Here, they're giving you those same problems, but in terms of this notation. So let's take a look at something of that nature. Now, actually, I'm going to say that's estimates. Yeah. This thing, find an approximation. Yeah, so the first few problems up here are just Riemann sums, right? Rectangles. This fella is asking you to actually use the limit definition of the integral to evaluate the integral. So let's take a look at something like this. I'm going to change the numbers just a little bit. Use the definition of the integral to evaluate. We'll say integral from, what do we want to do? Let's go from 8 to 10. And let's look at the function. That was about 5 minus 2x dx. So this really isn't anything new. You just have to interpret it correctly. The idea here is that instead of saying find the exact area under 5 minus 2x from x equals 8 to x equals 10, I'm just stating that same thing in terms of the new notation. So remember, this object is the exact area under this function from this x value up to this x value. So let me just state it like that first. This is the, well, fuck it, no, let's just jump in. So this is by definition, limit n to infinity, sigma I from 1 to n, f of xi times delta x. Now here my function, f of x, is 5 minus 2x delta x is always b minus a over n. So this is b, this is a. So this is b minus a over n, which is 10 minus 8 over n, which is 2 over n. And then we use that to construct our xi's. Xi is always a plus I delta x. A here is 8. Delta x here is 2 over n. So this is 8 plus I times 2 over n. And you can simplify that just a little bit. That's 8 plus 2I over n. So these are the various pieces that we need to plug in to this recipe. So let me kind of cordon this off. And we'll say, okay, this is equal to the limit as n goes to infinity, sigma I from 1 to n, f of xi. Let me just plug in the xi's for the moment. That's f of 8 plus 2I over n times delta x. And delta x is just 2 over n. In my next step, I'm going to see what this object right here is. So f of x is always the function that we're working with, 5 minus 2x. So I need to plug 8 plus 2I over n into x here, right? If I want f of 8 plus 2I over n, and this is f of x, then f of 8 plus 2I over n is what I get when I plug 8 plus 2I over n in for x here. This is the limit as n goes to infinity. Sigma I from 1 to n. I'm going to put this all in parentheses. Have 5 minus 2 times 8 plus 2I over n. And all of this is being multiplied by 2 over n. So this is the apparatus I need to evaluate. And in order to evaluate this, I'm going to distribute everything out here and combine like terms. I'll split up the sum and then use some summation formulas. This is probably the hardest problem in the homework set. That's why I'm wanting to look at it here first to make sure that you are comfy. It's really something from last week, just given in this new notation, but I know that working in this sigma notation is a challenge. They're certainly not interchangeable. The integral is defined in terms of the sigma operator, and the pieces do kind of match up. But the idea here is that this problem asked us to use the definition of the integral given in this theorem to evaluate the integral. So the definition of the integral is the limit of the Riemann sum. So what we're being asked to do there, what we're being asked to do there is evaluate the integral by first writing it as a Riemann sum. So we begin with the definition. This is the definition of the integral. And then I start plugging things in. And our goal is to evaluate this. It is true that down the road, I will give you another way to evaluate things like this. There is a slicker path. But just like you need to learn to work with the limit definition of the derivative, you need to learn to work with the limit definition of the integral. So within my parentheses here, I can clean up and distribute. This is minus 16 minus 4I over n all times 2 over n. Here I'm just distributing the 2. 2 times 8 is 16. The 2 is negative, so when it hits this guy, it becomes negative as well. 2 times 2I over n is 4I over n. So they're defined in terms of each other. Mackenzie has a good question in chat, right? That sigma and integral notations are kind of equivalent. It's not true that they're interchangeable. It's just true that one is defined in terms of the other. The integral is defined in terms of the sigma. So 5 minus 16, those are like terms. So we have lim n to infinity, sigma I from 1 to n. 5 minus 16 is negative 9. So I have negative 9 minus 4i over n, all times 2 over n. Well, remember, it's just the definition, right? So the fact that I starts at 1 here and ends at n, that the index of summation runs from 1 to n, means that this thing is Rn. That was what made Rn different from Ln. Ln started at 0 and ran to n minus 1. So this whole object is Rn, and it will always be that way. When you're evaluating an integral as a limit of a Riemann sum, the Riemann sum we always use is Rn, so the sum will always start at 1 and will always end at n. There are lots of other summation problems that exist, but if you're defining an integral, it will always begin like this. So from here, what I want to do is get to a place where I can use my summation formulas. We could use Ln, but the calculations are just a little gnarlier. If you use Ln, then I starts at 0 and ends at n minus 1, which makes the summation formulas a little bit more complicated. So the reason we choose to use Rn here is because it gives us a simpler summation formula at the end. Remember, all those summation formulas I gave you, they all start at 1 and end at n. If we used Ln, then our sums would start at 0 and end at n minus 1, which means the summation formula I gave you wouldn't apply. We would need to cook up separate summation formulas for those. So there's a lot of convenience in saying we're always going to use Rn to define the integral. And it certainly doesn't hurt anything. There's no loss of generality. If you use infinitely many rectangles with right endpoints or infinitely many rectangles with left endpoints, you'll get the same result. The big deal is the infinitely many, not the left or right. So if I want to get to a place where I can use my summation formula, I need to distribute this 2 over n and split up the sum, then pull out anything that doesn't have any i's in it. So my next line would look like this. If I distribute the 2 over n, I'd call this negative 18 times 1 over n. And I would call this minus 8i, right? The 2 and the 4i make 8i, and then there's an n downstairs here and an n downstairs here. I'll write that as times 1 over n squared. Because remember, my goal is to pop out anything that doesn't have an I in it. So I would prefer that these aren't mingled together, although you could write them like that. Next, I split up the sum. This guy is fundamentally different from this guy. This guy has an I in it. This one does not. So they'll need to be handled separately. So I'll have sigma I from 1 to n, negative 18 times 1 over n. And it would be healthy, I suppose I should write the negative 18 in parentheses like this if we're being careful, just to make sure it's clear that this is multiplication. And then I have minus sigma I from 1 to n, 8i times 1 over n squared. And this sum will be treated differently. There aren't any i's here. So everything here is constant with respect to the sum. There's only one I right here. It's being multiplied by 8 and also being multiplied by 1 over n squared. So I can bring the 1 over n squared and the 8 out of this sum. I can bring everything out of this sum, and what's left would just be a 1. Think of it like factoring. we're factoring out. So I can factor a negative 18 over n out from that first sum. And what's left would be sigma I from 1 to n of 1. And then I can bring an 8 over n squared out from the second sum. So I'll have minus 8 over n squared times sigma I from 1 to n of I left in the second sum. And these two objects, sigma I from 1 to n of 1 and sigma I from 1 to n of I, are the two first summation formulas we have. I'll see what those are. So remember the rule, we talked about this when we introduced the sigma notation. I'll write it over here. So the rule that Joe's asking about in chat there, 1 to n of some constant times some function of I, is that constant multiples can pop out. As long as k doesn't depend on I. So the sort of multiples that can pop out are anything that doesn't have an I in it, right? We'd normally use the word constant. We would say it's constant with respect to the sum, because the sum is being done over the index variable I. Anything that does not have an I in it is a constant with respect to the sum. In other words, doesn't depend on I. So yeah, over here, the 18 and the 1 over n, those don't have any i's, so they can both come out. And over here, the 8 and the 1 over n squared, those don't have any i's, so they can both come out. It's important that they are multiples, that they're, that the thing that's going on here is multiplication. But it's this rule, which was a part of the linearity of the sum. And then
But I thought 8i depended on I.
8i certainly does. That's why the I remains. The I stayed inside. The 8 doesn't depend on I. 8 is definitely just a constant, right?
Yes, sir.
So the I stays in. You're 100% right. He cannot come out. Pulling out the I would be incorrect. He is stuck in there because he is not constant with respect to the sum. But the 8 that's multiplying him can come out. And so can the squares. Yeah.
All right. Thank you.
Of course. Of course. So the next thing we need to do is use the appropriate summation formula for this thing and for this thing. The first one, even if you didn't have the summation formula handy, you could probably figure it out. If I add 1 to itself n times, I get n. But the summation formulas that we need here, sigma I from 1 to n of 1, this is just 1 plus 1 plus 1 plus 1 plus 1 n times. So that's going to be n. And sigma I from 1 to n of I itself, this is 1 plus 2 plus 3 plus 4 all the way up to n. This turns out to be n times n plus 1 over 2. So at this stage, we're ready to employ both of these. This one I will plug in here, and this one I will plug in here. So that gives me lim n to infinity negative 18 over n times this guy is just n minus 8 over n squared times n times n plus 1 over 2. And now all the hard work is done. And it is admittedly hard work, right? Again, I'm doing this problem because I think it's probably the first one you'll run into that is challenging. The n's here cancel. Over here, though, we're going to have some actual work to do. You can cancel one of the n's. This will become lim n to infinity 18 over n times n. That's just 18. So this is going to be negative 18. Here I have n times n plus 1 upstairs and n squared downstairs. So this n can cancel with one of these n's. I'll have minus 8 over n times n plus 1 over 2. And in that same way, I can cancel the 8 into the 2 because these are being multiplied, and we always think of fractions as having their tops and bottoms in parentheses. So 8 really is a factor of the top, 2 really is a factor of the bottom, so those factors can interact. So we get negative 18 minus 8 over 2 is 4. So this is 4 times n plus 1 over n. And that's as much as we could possibly hope to simplify this before taking the limit. Then n to infinity, negative 18, minus, and we can distribute the 4 up here if we want. This is 4n plus 4 over n. And there's a handful of ways you could approach this limit, right? This is the only part where we need to do some work. As n goes to infinity, the top and bottom both go to infinity. You could use L'Hopital's rule if you wanted. But I think the easier path is to renormalize. If you divide top and bottom by n, right here. So that negative 18 over n is this piece. So this piece is this piece. And then my summation formula says that the sum from 1 to n of 1 is just n. So this piece is this piece by this summation formula. So the negative 18 over n is just coming along for the ride. And then the sum from I equals 1 to n of 1 itself is just n. And then in my next line, I cancel the n's and I just get negative 18 there. Same sort of thing I did over here. Here, the 8 over n squared comes along for the ride. This 8 over n squared is this 8 over n squared. And this sum, the sum from I equals 1 to n of I, becomes n times n plus 1 over 2, according to the second summation formula here. Cool, cool. All right, so as n goes to infinity, what does this second piece do? This is a 2.6 problem. The way we learned to solve these back in 2.6 was by renormalizing. So if I divide in this fraction, top and bottom by n, I get 4 plus 4 over n divided by 1. Right? Every term gets divided by n. 4n divided by n is 4. 4 divided by n is 4 over n. N divided by n is 1. And now as n goes to infinity, 4 over n goes to 0. So we get negative 18 minus 4 plus 0 over 1. Which is negative 18 minus 4, which is negative 22. And that's the game. So in passing from this line to this line, I used our renormalization trick. For limits. For limits at infinity. Specifically, I divided top and bottom by n. So remember the renormalization trick, you divide top and bottom by the largest power. The largest power of my variable anywhere in this expression is n, just n to the 1. The top is linear, the bottom is linear. So if I want to kind of rescale this expression so that I can tell what happens as n gets bigger and bigger and bigger, you divide out by that fastest growing term. So this term would become just 4 when I divide it by n. This term would become 4 over n when I divide it by n. And this term down here becomes 1 when I divide it by n. You could also use L'Hopital's rule. Or if you remember that trick from pre-calculus, the way most people learn this is that if the degrees of the top and bottom are the same, then you just take the ratio of the lead coefficients, right? That's the lazy way to take limits at infinity, is if you're going to infinity and the degree of the top matches the degree of the bottom, here they're both degree 1, then you just take the ratio of lead coefficients, which is 4/1, which would be 4. That could get you there faster, but it's technically not rigorous. All right, so this integral is equal to -22. The integral from 8 to 10 of 5 minus 2x dx is equal to -22. That's what we have shown. I'd like to take a second to point out that we could have done this geometrically. We could have done this by interpreting it as an area. Five minus 2x is a line. It's a line with y-intercept 5 and slope -2. It crosses over the x-axis when, let's see, x is equal to 5/2. And what we were doing was finding the area bounded by this function and the x-axis from 8 to 10. Now 5/2 is 2.5. So 8 is like way out here. 10 is like way out here. So the area we were finding was this area. Which all lives beneath the x-axis. So it's not surprising that this is negative. And if you wanted to, you could draw this picture, chop this region up into a triangle and a rectangle like we did in class on Monday, and calculate the area in that fashion. That would have worked as well. Last time we did see a number of problems like this, and I'd like to point out that there are a handful of those in your homework. So the majority of these first few problems are just getting you comfortable with the definition. The first few problems are just straight up Riemann sum problems, exactly like the problems from last week, only now your functions are allowed to sometimes be negative, right? You've got negative outputs now. This next guy asks you to take this limit and write it as an integral. We did one of these last time also, remember? The xi plus sine of xi, same thing. That's those two. This fellow is like the one we just did, and these are probably the hardest ones, where you have to use the definition of this integral, write it as a limit of a sum, and then evaluate that limit. That's the trickiest bit. So number 5 has you doing that. Number 6 has you doing that as well. First, on number 6, you're going to use a Riemann sum. You're going to use a finite Riemann sum. You're going to use R8 to approximate the integral, and then you're going to do the same thing we just did. All right, you're going to actually write out the definition of the integral and evaluate the sum. Again, the function's not too bad, and you should be getting comfy with this by now. Expect this problem to take about 30 minutes. Okay, expect it to take a while. Number 7 here, this is a lot like the ones we were doing in class where you had to interpret the integral as an area. You need to do geometry. So the integral from 0 to 16 of f of x dx is the area under this curve from 0 to 16. So it's the area of this region you see me outlining here. In part B, you're asked to find the integral from 0 to 40 of f of x. So where's 40? Is it halfway between 32 and 48? Yeah, we're taking steps of size 8, right? So the integral in part B that you're calculating is the area of this whole region here. And you see me outlining with the mouse now. And again, you can use geometry. You can break this up into rectangles and triangles. I would break it up into a little triangle here, a little rectangle here, a little rectangle here, and a little triangle here. You can calculate those areas and add them up. That will give you this integral. And you do the same for the remaining ones. This, again, same sort of thing. This time you've got a little triangular region, and you've got a semicircular region. So you're going to need to use the formula for the area of a circle, just like we did on the last problem on Monday. And then the remainder of these interpret as an area, interpret as an area, interpret as an area. So you have to draw the graph. Instead of them giving you the graph like they did here and here, on these guys, you have to draw the graph. There are some properties of the definite integral, and problems 12, 13, and some of the later ones require you to use those properties. So let's talk about those. These are actually really neat. The first two, the integral is linear. So the integral from a to b of some constant k times f of x dx is equal to that constant k times the integral from a to b of f of x dx. And this is for any constant k. And what we mean by constant in this context is it doesn't have any x's. It's the kind of variable here is x, just like the variable is I in your sums. The variable in the integral is x. So constant multiples pop out of integrals. This can be a very useful fact. 2. The integral from a to b of a sum of two functions, f of x plus g of x dx, is equal to the sum of the integrals. So that's integral a to b f of x dx plus integral a to b g of x dx. And as is almost always the case when you're looking at these sort of things, if it works for a plus here, it works for a minus there. These two properties together are called linearity. The integral is linear. So it's called a linear operator. And we talked about that earlier. The derivative is a linear operator as well. ddx, the differential operator ddx, is a linear operator in the same sense. Some other really important properties. If a is less than c is less than b, in other words, if c is a number between a and b, then the integral from a to b of f of x dx can be split up as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And this one comes with a picture. Here's the graph of some generic function f of x. Here are the x values, a and b. So the integral from a to b of f of x dx is all this area under here. But if I were to look at some number C in between A and B, like this, then the area from here to here, that's the integral from A to C of f of x dx. Because it's the area bounded by f of x and the x-axis between A and C. And this guy over here is the integral from C to B of f of x dx. So the total area is the integral from A to B of f of x dx. And that's equal to the sum of the two little areas, integral A to C f of x dx plus the integral from C to B f of x dx. This is the first little area. And this is the second little area. This fact is surprisingly useful, right? The fact that you can take an integral and split it up over its middle, over any number between A and B. This means you can take two things like this and combine them into something like this, or you can take something like this and split it up into two pieces like this. It's especially useful for piecewise functions. Okay. So let's take a look at a problem where we employ this stuff. Yeah. I think the first two guys are the sort of most intuitive ones to apply. So we'll start with a problem that uses those. Some more paper. Let's use the fact that the integral from 0 to 1 of x cubed dx is 1/4 to evaluate, and I'll do a few things here. The integral from 0 to 1 of 5x cubed dx. And I'll do integral 0 to 1 of 2x cubed plus 3 dx. Go back to the properties of the integral page. There we go. Okay. So what do? They tell me that the integral from 0 to 1 of x cubed dx is 1/4. And then they ask me to cook up this thing. I could build a Riemann sum for this thing. I could jump in as though I had no other information, use the definition of the integral as the limit as n goes to infinity of sum I from 1 to n, and really put on my big boy pants and go for it. But is there a better path? Is there some way I can use the information they gave me? I think I heard something there. What was the thought, Trevor?
You can take the 5 out.
Hell yes. That 5 is a constant multiple. So he can pop out, and I get 5 times the integral 0 to 1 x cubed dx. Somebody else, why is it useful? Why do we want to pop the 5 out?
Then you can plug the 1/4 into the x cubed dx.
Perfect. This thing, this whole thing, integral from 0 to 1 of x cubed dx, that whole chunk, I know is equal to 1/4. So this is just 5 times 1/4, or 5/4. Way better than writing out the Riemann sum, right? Way better. All right, what about this guy? Am I screwed? Do I need to go back to Riemann sums here, or is there something else I can do?
You can break it apart into 2x cubed, or the sigma of 2x cubed plus sigma 3.
You've got the right idea. You're saying the correct things. I would just swap the word sigma for integral.
Integral,
So,
sorry.
yeah, no, don't feel bad. You're good. So we're going to do exactly as Adrian recommended. We're going to use the second property, which says we can take integrals and split them up over addition or subtraction. So inside here, I've got some addition. I can split it up as the integral of 2x cubed. And you always write the dx at the end. I know this might seem like a silly thing. We might not fully understand where the dx is coming from. Remember, it's like the delta x in your Riemann sum. It's just an infinitely small delta x. It's also going to have a deep meaning down the road. So never skip writing the dx. Always write the dx. And then we have plus integral 0 to 1 of 3 dx. What can I do from here? This doesn't quite look like something I know immediately.
You can take the 2 out.
Good. The 2 can come out of the first integral. Okay, what about this other guy? What am I going to do with him?
Could you take the 3 out and just have dx at the end, or is that like
You
pointless?
absolutely can. Yep. And it's just like popping everything out and having a 1 left inside the sigma. Same sort of thing. So I would even write this as 1 dx. That's totally kosher. Now this guy, the integral 0 to 1 of x cubed, I know that. That's 1/4. What about this guy? They didn't give me a formula for this. Am I screwed? Let's put in the pieces we know. We know that this piece, integral 0 to 1 x cubed dx, is 1/4. And then I know I'm going to have plus 3 times whatever this is, but I don't know what this is yet.
Going back to the earlier problem, didn't we have the integral of I to n of 1? And didn't that come out to be n?
It's true that the sum from I equals 0, or the sum from I equals 1 to n of 1 is equal to n. Yes. And we could, if we wanted to, write this as a limit of a Riemann sum and then use that fact, because the fact that there is just a 1 in here would correspond to there just being a 1 inside the associated Riemann sum. But there's an easier way to do this. What if I interpret this using areas or geometry as an area? This little integral right here, the integral of 1 dx from 0 to 1, would be the area bounded by what function and the x-axis? What's the function inside my integral here?
Isn't
Would
that
that
like
be y equals 1?
Yeah, don't think too hard. It's definitely just y equals 1. Well, f of x equals 1. And we're finding the area as x goes from 0 to 1. So here's x equals 0, and here's x equals 1. So what is that area?
1.
Yeah, it's just this little 1 by 1 rectangle, right? So this piece right here, the area is equal to 1. So the integral from 0 to 1 of 1 dx is just equal to 1. So this is 3 times 1. So I get 2/4 plus 3, which is 1/2 plus 3. And on a good day, I would want to write this as a single fraction. So this is 6/2, so this is 7/2. And that's it. Not too bad, right? The good news is we're going to eventually have a lot more things like this. We're going to have ways to evaluate integrals regardless of the bounds for any power of x. And then using these sort of things, we can split up and evaluate integrals of any polynomial. But we're not quite ready to do that yet. We need to first learn about antiderivatives. Let me see if there's anything else we need to address here. No, you guys can do this. C, yeah. All right, you guys should be well. Oh, there is one more thing. Yeah. Okay. So Friday, I will teach you about antiderivatives. And then we will be ready to start moving towards more sophisticated methods for evaluating integrals. There is one more theorem we need. Homework problems require use of this theorem. If the integrable function f of x is bounded below by little m and above by capital M on the interval AB, then little m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to big M times b minus a. This is one of those things that might look like meaningless gobbledygook until you interpret it. So you need to think a little bit carefully about what we mean by bounded below by little m and above by big M on the interval AB. Let's draw a picture. I'll go ahead and prove this for you. The proof is very simple. It just follows immediately from the picture. When we say a function is bounded below by some number and above by some other number, what we mean is that the function, the y values on the graph never get smaller than little m and never get bigger than big M anywhere between a and b. So let me do it like this. So say this is my function f of x, again meant to be pretty much just a generic function. We know that the integral from a to b of f of x dx is all of the area in here. Okay, I'm not an artist, but you get the idea. This is the object in the middle of the inequality here. An upper bound for f of x on the interval AB would be whatever this y value is. Anything larger than that would work as well. But let me come in here and say, okay, this function is definitely bounded above by this line. This is capital M. And bounded below by anything that is like down here. This would be like little m. And now if we think about the areas, actually, shade this guy purple if I can. Some judicious use of color never hurts. Okay. So would you agree that f of x is always bigger than little m, at least between a and b? Yeah, the graph of f of x is like always above the line y equals little m. And similarly, at least between a and b, f of x is always smaller than big M. Now think about the size of the pencil area compared to the size of the purple area compared to the size of the blue area. The blue area is clearly the largest because the other two fit inside. What is the blue area? Well, it's its height. It's a rectangle, right? This is a rectangle. So the blue area is this height times this width. The height is capital M, and the width is B minus A. So this guy is the blue area. Similarly, if you look at the little rectangle down at the bottom, its height is little m, and its width is also B minus A. And clearly, the little purple rectangle down at the bottom is smaller than the pencil shaded area because the pencil shaded area contains it. It fits inside the pencil shaded area. So he has to be smaller than the integral. And then the pencil shaded area is between the two, fits inside the blue, so it's smaller than the blue, but the purple fits inside it, so it's bigger than the purple. And that's the proof. So this is a surprisingly useful theorem, especially when you're trying to understand integrals of functions that are difficult to work with. You can always find a little m and a capital M like this for any continuous function. Remember, continuous functions always attain a min and a max on any closed bounded interval. So the most judicious capital M would be the absolute min for f on AB. It would actually be a little bit lower. And the most judicious choice of little m would be the absolute min for f of x on this interval, which would be a little bit higher. But any m which is larger than all the y values on the graph will work for capital M, and any m which is smaller than all the y values on the graph will work for little m. And oftentimes we want to try and bring these two in as tight as we can. And that will give us our best possible approximation here. So this is a theorem you're going to need to answer. No, don't do it, don't do it. This is what you're going to need to answer. There is similarity to the squeeze theorem here. Yeah, you're sort of squeezing the area you want between two areas that are easy to calculate. But we don't begin by setting up an inequality using algebra tricks the way we do with the squeeze theorem. But intuitively, it has a lot of similarity to the squeeze theorem, I agree. You're going to need this result for question number 19 here. Is there anything else that you're going to need specific hints on besides the antiderivative stuff? No, this is the same sort of thing again. Here they give you a sum and they ask you to write it as an integral. You're just using that formula, given a sum, write it as an integral. I think that's all. So the only thing that's left for us to talk about this week is antiderivatives. And those might seem like they have nothing to do with this area business, but I assure you they do. And I will show you the connection between those two next week. So on Friday, we're going to learn all about antiderivatives. And then the following week, we're going to begin learning how to calculate integrals using more clever, sophisticated methods than what we've been doing. Any questions for me here before I let you guys go for the day? Alrighty then, I'm going to go ahead and end the lecture. If you do want to talk about anything, of course, remember today is the withdrawal deadline. If you're having a hard time making any decisions, if you want to talk about anything, just come by office hours. Happy to chat there. Or you can send me a Canvas message, an email, whatever you like. Take care, guys.